Assalamualaikum warahmatullahi wabarakatuh. Now we'll talk about the other types of secondary effect in BJT. So in BJT, so if you plot the graph of beta, this is HFE or the beta against the collector current, and we can see a trend whereby there are three regions over here. You can see the region A. No, wait a second. Region A, region B, and region C. Okay, so in region A over here, it occurs at low collector current. So at low collector current, you can see as if the beta is increasing with increasing collector current, and at the region B, whereby in region B over here it's nearly a flat constant, whereby any changes of IC doesn't change the beta. And then finally region C over here, okay, whereby as you increase the collector current, you can see reduction in the beta. So what's happening over here? First of all, let's talk about region C. Region C is where the Kirk effect happens. Okay, Kirk effect. Let me type this. This is the Kirk effect. So whereby as you increase the collector current, the beta decreases, and there's another video on that, how or exactly what happens in during Kirk effect. So the region B, we say here roughly a constant value, which means this is the ideal situation where if you increase IC, it shouldn't changes your beta. Beta should remain stable and the same, regardless of the value of the collector current. So this is the ideal, this is the operating region that we want. But also before that is region A. Region A is where is region where at low collector current the beta increases to the desired value of the beta. So let's see here what's actually happening in now we'll discuss about the A. In region B is the one that we discussed, is the ideal working of a BJT. Okay, in fact we have another video. Now we'll talk about the region A. So we can see in this graph, basically the beta changes with IC according to the values of the collector current. So at low collector current, which is at low collector current, at low collector current, the combination current dominates. So okay, brothers and sisters, we can see here IC. Sorry, bukan. Let me rub this off first. Okay, beta. Okay, maybe I want to make it smaller. Beta equals to IC over IB, right? This is what we know. The gain of the transistor is a function of the collector current and the base current. Now the case is we are at a low collector current. At low collector current, the base current dominates. How is it possible? Because if the collector current is high, then any changes in the base current will not make any significant difference to the beta, right? If the IC is significantly high, a small perturbation or changes in IB will not affect much the beta. But if the IC itself is low, if the collector current itself is low, any changes in the base current will affect the beta. Okay, so let's see how does this affect, why in the end it seems that the collector current is increasing, and the gain is increasing with the collector current. Actually, okay, let's see it has to do with the defects in the transistor. Okay, So it has to do with the defects in the transistor. Let's go back to this equation here. For a particular collector current and at low collector current, therefore base is very much the gain will depend on the any changes in the base current. So let's say, so therefore the base current, if you remember before, how do we get the base current? One of it is due to recombination of the carriers inside the base region. So let's say in the base region we have any most of the semiconductor will have defects. So here's a energy band diagram of the semiconductor. We have the conduction band and the valence band, and we have defects trapped inside the structure. So so how do we get so we can get generation current, we can get band to band like this, or you can also have generation recombination current through traps like we discussed before here. So the electron will be excited to the trap, and then the trap to the conduction band, therefore we have a lot of more of free carriers, therefore will increase. So this base current is very much affected by the generation recombination current which is also is a function of the defects. Now so at low collector current and with the same amount of defects, right? So throughout this if you look at excuse me, if you look at this graph over here, if you look at the graph over here, we can see that the graph over here, as we increase the collector current, the beta it looks as the beta increases because during this collector current, the low collector current, the defect doesn't change, the defects remains the same. So it means if you have 3 defects over here, it will still remains the same. The only difference is as we increase the current, these defects can be filled. For example, you can have electron that go over there and then will stay here, right? And if there's a lot of current, so if this is keep on going, as if the traps will remain filled. So therefore, as if you can see that the defects, the effective defects or traps reduces. So when that happens, so if we reduce the number, as you can see in the equation over here, if we increase, so at very low collector current, we can see that the defects, the effect of defects is higher or bigger or larger in the effects of it. So therefore when that happens, IB will be a high value. When IB is a high value, what happens to the base? So what happens to the gain? The gain will decrease. So that's why we can see here at low let me click here. At the low collector current, the beta is low. See, the beta value is here low because of the generation recombination current dominates due to defects. However, as we increase the current, the collector current, we can see the effects of defect filling of the traps inside the semiconductor, and therefore, as I mentioned, as if we see the effective number of traps decreases. So let's say from 3 it becomes like effective only 1, hence therefore the generation recombination current reduces. So if the generation recombination current reduces, and this will overall will give a higher value of the gain. So you can see that's why as we increase the collector current, the gain increases. And this effect at A is actually due to defects in the structure. Okay, I hope you understand. If you don't, you can ask me question in the class. Okay, thank you.